All right. What I want to do with this, of course, is discuss the impact of this particular component of the life cycle, like extraction, on both industrial ecology and the circular economy. Obviously, I've gone through this in other classes, but I'd like to essentially give the spin that essentially it needs to in terms of what we do in terms of trying to eliminate waste and how the circular economy actually is going to significantly impact extraction. So with that, setting the stage, let me give you just a little bit of background in terms of my own experience in this particular area. Um, Now, I think it's been estimated that for pharmaceuticals, it looks like over 98, 99% of all compounds that are utilized in the manufacture of medicines come from petroleum. The issue, of course, is that petroleum has a limited life cycle. It's not going to essentially be here forever, and therefore we need to be thinking about what it takes to live without petroleum. So part of my initiative was to essentially start the transition, urge the transition to think about deriving those same starting materials, those building blocks from plant-based starting materials. Now, the first pushback I got, of course, was it's very costly. It's beyond our remit. Let's let somebody else do this. This isn't for us. Um, and, at some level, I understand that argument. However, we felt the solution was to start looking at the supply chain, trying to find organizations that recognized that there was a biological starting point for a lot of the compounds we use and whether or not we could use that. So, and again, it's one of those issues that requires sort of a constant review, a constant effort, continuing to push on that. The other one, of course, was a situation where we actually had renewable starting materials. We had a new cancer fighting drug called topotecan, and it did require a starting material from a biological source, which was great. It was found both in China and in India. They had very different names in both of those countries. And we looked at this and recognized that in terms of the natural sources, we needed a significant quantity of this material. Just like fisheries, like forestries, if all we did was rely on that naturally occurring material, we could easily extinguish that availability of material within a few years. And so as a result, I essentially highlighted this to the folks within R&D and manufacturing, recognizing we needed to start to farm it. And really not to touch the natural sources. And again, once we demonstrated the mathematics on this, I think they understood it. And of course, they went to make the investment in this particular farming approach. But again, it shows that in many cases, manufacturing, and again, it's not arrogance or conceit, it's literally just a lack of awareness. And so with a little input in terms of awareness, we think that's very important. So that's one of the strengths, I think, that an environmental industrial ecology approach brings to this argument. Now, before we go into some of the specific examples I'd like to talk about, let me talk about quantifying sustainability in terms of what happens with resource limits. And there are a lot of different factors here. Of course, one of those factors is how much is being consumed. And not only is it consumed in terms of what happens now, but what happens if there was an equitable consumption? What happens if we were driven either by non-economic or economic factors? And what does that do in terms of the global availability to people for a particular resource? And so the question is always out there, how do we allocate this? And obviously we have an economic model right now, but in terms of equity, utility, certainly from the global north to the global south, doesn't always work. So there's a need to think about a different approach in terms of how we allocate those resources. And again, it comes in a number of different varieties. There have been discussions and papers written on just literally a strict allocation, either country by country, predicated on population, that essentially doesn't necessarily take into account the issues of economics. That literally they have this allocation, And, obviously they'll pay what they can, but there's a different economic profile. That does not necessarily encourage private companies to invest in this sort of extraction process. And so therefore, obviously it has to have some sort of subsidies from other sources, usually, again, the developed countries to undeveloped countries. The other, of course, is how do we deal with our current consumption pattern relative to natural limits? Are there substitutions for those materials? Or, as we discussed, can we find a way to start to capture the wastes of those materials in a way that allows us to recover and then reuse in a regenerative fashion and avoid the impact it would have on extraction? And of course, how do we actually develop and implement the corrective actions I just mentioned? Now, the next step, the next issue broadly, I know some of you have had this, is the difference between a resource and a reserve. Very simply, the resources, of course, is all the material that you believe exists on the planet. The problem is that material in many cases does not exist at the sort of quality or the concentration that makes it economically feasible to extract. And that's where the reserves come in. The reserves really is the number of materials that are available, the quantity of material that's available that can be economically extracted from the planet. And so therefore, as you can see from this diagram, this cartoon, reserves in many cases is a much smaller number relative to the total resources out there. And it can range in terms of what you have with respect to different minerals, metals, petroleum, that sort of thing. So there may be more petroleum reserves out there, resources that we can possibly extract economically. Now, one of the things about that is that as those reserves become smaller and smaller, the economic pattern changes. And if people really need those resources, those reserves, they will be willing to spend more and more money. So as a result, that box is not fixed. It is quite variable in terms of its effect. Of course, the other component that changes that is a new find, a new exploration, a new discovery that allows that reserve to essentially be recalibrated, redetermined. So with those two, parameters, you need to recognize this is always very much a fluid argument. Basically, however, you have to recognize that at some point in time, we're going to hit a natural inability to extract that resource. And therefore, the reserves literally will dwindle to nothingness. And it just is a reflection on the limited amount of materials that exist on the planet. We are a finite planet. Now, let me use copper as an example. If you look back in terms of the early reserves, going all the way back to 1770 in the UK, you saw that the ore grade for copper was about 12%. Australia, my goodness, it got up, in the late 1800s, it rose well over 24, 25%. But you can see it's starting to dwindle as we continue to extract more and more copper ore. The quality of that ore has been diminishing. So at present, the copper ore has moved from, say, 12% or 25% to 0.6% on average around the world, which means you need 166 kilograms of ore to obtain a kilogram of copper. Now, the other component of all of this is the consumption rate. And of course, consumption is a factor by population. So you need to look at what is the population growth going to be in terms of how that impacts the future. So roughly by 2020, the estimates were that the population hit about 7.5 billion, by 2050, 8.9, and hopefully median population projections are that by 2060, we'll flatline at about 9 billion and stay there and possibly decline a little bit. Now, one way to look at the resource demands for this population is do an incremental analysis for each of those population changes. But I'd like to, again, pursue a more simpler approach in terms of what we need to do. But that orange line, of course, is the median population that I mentioned before. So let's assume that median will hold true for our consumption of resources. And what I'd like to do is look at resource limits. And I think you'll have a homework assignment for this. So the fundamental question is, what is the number of years that a particular reserve will exist. And you can talk about, you can pick copper, petroleum, nickel, lead, whatever the number is, and try to, find out what the global reserve would be, usually estimated by the United States Geological Survey, so the USGS. Now, what we want to do is to find the current global annual extraction rate. So if that number is provided, if you can Google this one through, and we're fine. What I suggest we do is to not just look at our current extraction rate, but try to prorate this so we get some sort of average between, say, now 2021 and 2060. Now the midpoint, of course, is about 2040, and so therefore determined, we had this from the prior graph, that by 2040 the population should be about 8.6 billion. So let's use that 8.6 billion divided by the current population of 7.5 billion. So the extraction rate for 2040 can be multiplied by 1.15 to get you a revised number. Then, of course, take that number and divide it into the global reserves, because you have amount of, say, tons per year divided into tons will give you years. That will give you the number of years available for your reserve, with, again, a constant consumption rate, no change in the products and materials. Again, a lot of simplifications here, and we'll go in a second. Now, the question is going to be, what if you can't find the extraction rate, but you do find the consumption rate? And this is, relatively straightforward thing. If you can find the consumption rate, you'll need to also find the recycling rate, because the recycling rate will decrease the amount of extracted materials that are needed. Aluminum would be a good example. If 30%, 40% of aluminum is recycled, obviously you don't need to extract aluminum from the soil, from the ground. So same sort of thing. The extraction rate is consumption divided by 1 plus the recycle rate, say 1 plus 0.33 as an example. So 1.3 divided into consumption gives you your extraction rate. Multiply that again by the population difference of about 1.15, and then use that for your annual yearly consumption. Now, again, as I mentioned before, this is a simplified approach. And we can certainly be a lot more sophisticated and use a lot more complexity in terms of our approach. But you also have a lot of complexity just in the system of global exchanges within respect to the economic, social, and environmental systems we have there. Little is included in terms of any negative externalities. And at the bottom line, of course, is that the complexity will yield only marginal benefits in terms of our understanding of the fact that resources are limited. So this is why I propose this particular simplified approach. Now, the limitation on simplicity is that of equity. The analysis does assume equity, which certainly is not realistic. Resources are usually owned by individuals or corporations. They tend to sell it to the highest bidder. There are other options, as I mentioned before. There can be a global treaty, allocations, regional allocation rates are out there. But as I said, right now, allocation is left to market forces. We may come to a time where a global treaty may be required in order to ensure some level of equity, especially if it's a key and critical need. I want to talk a little bit about water as well. Water, of course, is required for drinking, food, health, and recreation. Bottom line, of course, is it's required for life. Now, climate change already has a significant impact on water availability. More floods, more droughts. Essentially, you just go to the extremes with the impacts on climate change. Now, of course, the bottom line is that 2/3 of the planet is covered with water, but only about 2.5% is fresh water. And much of that is locked up currently in ice or in groundwater. So, what we would need in terms of a volume would be a sphere about 35 miles in diameter to hold all of the water we have access to in terms of rivers and lakes. So it's not a significant amount. And as I mentioned, climate change is shifting weather patterns. Some areas are drier, some are wetter, floods, droughts. And of course, in both of those situations, you have limits in terms of the availability of water. And flooding sometimes is worse because you have contamination with the flooding, and you have a lot of water being present, but not a lot of it being easily available and readily consumable. So water availability is clearly a limiting factor in terms of developing people. It's also true for companies. Now, Coca-Cola essentially experienced a big problem in India. In Kerala, they had a bottling plant with a deep well. And when there was a drought, their well was deeper than the wells in their neighbors or farmers. And so they continued to bottle Coke, which of course was their prime business objective, but it essentially dropped the water table below what the other wells were able to access. And so therefore, they literally starved the community out of their water resource. That created a big pushback for India and for Coke. And as a result, at some point, India pushed Coke out of the country. I think they were able to get back in again. But nonetheless, there was a recognition by all water-based products that water becomes absolutely key and critical. So not only Coke, but Pepsi, Nestle Water, Miller, all the water bottling companies, the beer companies, all of those folks recognized that water was key and critical. And not just for water-based products, it's critical for all development. Fracking, electronics, pharma, water is essential to many, many industries. Now, there's also a concern for what is virtual water. And that is, again, the amount of water it requires to grow or use or generate a particular product. So the simplest example would be growing crops. You can grow your crop and sell that in a water scarce area. And there's a lot of virtual water, the amount of water it took you to grow that crop. Beef is a good example of that. And so you have to recognize that along with that particular export of a particular material to another country, there is amount of water that essentially is inherently bound in that in terms of its growth and development. So currently about 20% of the world's economy is produced in water scarce areas. By 2050, about 45% of the global GDP will be at risk. But water is not like other resources, not like other commodities. It is local, can't transfer it. It is typically undervalued. People just don't pay much for it, and they don't see it as having a great deal of value. It comes from the sky. It's everybody's. It should be free because that's how they perceive it. It is also seen as a human right in many circles, many countries. But of course, with that comes a lot of questions and a lot of problems, because if it's a basic human right, that means everybody should have as much water as they need, not necessarily as they want, but as they need. And so the responsibility of governments is to ensure that need is met. And of course, the bottom line is it's necessary for existence. Now, the other component of water is that there is this interaction with food and energy. And of course, the impact that climate change will have on all three of those. So you can see from this particular diagram that food, energy, and water are very much interdependent. And classically, as we can discuss, food is required to produce energy. Water is required to produce energy. Energy and water are required to produce food. And in some cases, food produces energy. The problem is that, from an industrial ecology standpoint, 58% of our energy is wasted. And worldwide, almost a third of our food is thrown away and wasted without being consumed. And that whether it's in the developing world or in the developed world, you can see that every day in terms of what happens, say, at Penn's cafeteria. A great deal of food is not consumed and not utilized. And obviously, that's something that we need to think about as a society in order to improve on that. So let me go on to the broad area of resources. And of course, the classic question that comes from a lot of people is, if there's a resource crunch, why do we have all the things we need, and why is gas cheap? And of course, part of the issue is that we live in the developed world. We live in a very rich country. And so therefore, that is available to us. However, it's at the expense of what happens around the world. Right now, we estimate that it's going to take about 1.5 Earths to support our present consumption, which raises the obvious question: how is that possible? We only have the one planet. How are we, supporting this type of consumption currently? And of course, part of the answer to that is the difference between assets and income. Obviously, we have a store of assets in terms of trees, fish, metals, some of which is being renewed every year. But if we are consuming, i.e. spending down our savings faster than can be replenished, in many cases by about 50%, what you're doing is literally withdrawing your capital. And therefore, at a certain point, your capital, i.e. your reserves, your resources, will be extinguished. And that's essentially where they're coming from in terms of that approach. Now, in terms of the World Economic Forum's global risk back in 2013, what they saw were two of the four most likely risks to the global economy were clearly climate change, but also water supply crisis. So energy and water clearly are going to be there. However, they noted that the scarcity of resources would be fourth among all top global risks. So they recognize that this is coming for the future. So the basic question is, if we ever get to a point where resources, and in some cases we have, when those resources are scarce to the point where people need it to survive, will we go to war over those resources? And if the answer sometimes is that that certainly is possible if we're not careful, if we're not thoughtful, if we don't understand a different approach. Now, that approach probably needs to accept the population growth numbers. Outside of something draconian, which no one's going to advocate for, the population growth is going to be what it's going to be. So therefore, we have to deal with the issues around both efficiencies, and we saw the waste before, but also innovation. We have to recognize that innovation drives these programs, so we have to be much more innovative in terms of a global society. And it also requires that we examine our strategic choices. And it gets back to recapturing valuable materials at the end of their useful life, i.e. the circular economy. And so a lot of people in this regard are thinking that the circular economy can be a substantial factor in terms of impacting our ability to be sustainable, to go forward into the future, allow our population to continue to grow, allow people to have the same standard of living that they currently have. The other one, of course, is a page out of the Industrial Ecology Handbook, and that is that they have to reduce consumption. Business models have to be more efficient, they have to eliminate waste, and they also have to generate products that don't encourage consumption. Fast fashion may be something of the past. We have to essentially find a different way to clothe our people in a way that is not necessarily so wasteful. So extraction, of course, impacts energy, environmental issues, social issues, human rights issues. But bottom line, of course, is that in all of these, there's system impacts. You can't hold any one of these in isolation. You look at its totality overall. So the big challenge for us is, what does extraction look like in a circular economy? Now, if we had an ideal circular economy where materials were, used materials were recovered and either recycled or refurbished, the impact that has on extraction will be profound. Now, there are going to be natural losses, and I don't think we were ever able to avoid that. And what that does, of course, is expand the amount of time that we have if we only rely on extraction to deal with the material losses in that circular economy, whether it be with the consumer or whether it be in terms of reprocessing material, to the point where certain materials just won't be able to be economically recaptured and recovered. So that fundamentally, I think, is the challenge we have, to look at the circular economy in a way that identifies opportunities for us to actually minimize the extraction, if not totally eliminate it. Let me talk about a couple of materials in terms of those impacts I think are important here. Oil, petroleum has to be the key issue. Clearly, oil has a big impact. It does create a geopolitical friction. It can essentially incite wars. It can also create alliances that, unfortunately, if not properly managed, can create wars. There can be environmental issues from oil in terms of oil spills. Just as we talked about before, there's going to be an issue about resource availability. BP has looked at the availability of petroleum and estimate that if our current reserves don't change, it looks like we'll only have till about 2067 to be able to extract oil at our current rate and our current usage. The other, of course, is that oil becomes the foundation for economic growth. We'll see some graphs later that demonstrate that with cheap oil comes economic booms. And with expensive oil, you have recessions and decline. And naturally, almost both directly and indirectly, it creates a a significant level of employment. That we'll have to think about that. Now, usually the answer has been to move from fossil fuel industries to renewable energies in terms of employment opportunities for people. And that may be the case. And whether or not that completely satisfies the employment needs out there will be something we have to determine. I also want to talk about peak oil. This again gets into limits. Back in '98, Colin Campbell essentially sat down and said, look, if we evaluate what we're doing, it looks as if that there's going to be a peak oil scenario somewhere, again, almost 10 years ago in 2010. And of course, with those supplies, more volatility, higher prices creates the potential for crash. However, if you curtail it and you reduce oil demand, the prices will fall and you'll have another boom. So you'll go through this boom and bust cycle strictly predicated on what happens with oil. And so, as I said before, it's a cycle with what happens with weaker recoveries and deeper crashes. The problem with this volatility is it has frustrated investments in renewable energy. It also has the potential to lead to wars between importing countries. Now, so therefore, the existing production of petroleum is dwindling with greater expense for extraction and difficulty in terms of finding new sources. Now, what will come to the rescue? Hopefully it'll be renewable energy or efficiencies. The problem, of course, is we've gone through this issue with respect to food. There's been the book by Paul and Jean Ehrlich called The Population Bomb, which essentially said we don't have enough food to feed everybody. And of course, Norman Borlaug came up with the Green Revolution, solved that problem for the short term, and essentially undermined this whole doomsday message. And so this whole discussion can be influenced by people looking back and saying, look, Ehrlich essentially came up with this whole scenario about problems with food. It's been resolved. We can do the same thing. And again, there will be alternatives. There probably will be remedies. Renewable energy could be out there. Nuclear energy could be out there. But nonetheless, the issue about petroleum is going to be limited. This is the, if you will, a graphical representation of what I mentioned before. It's a concept called energy return on energy invested. So the idea is it takes a certain amount of energy to recover those fossil fuels. That, of course, then reflects what we have with respect to the energy recovered. And so you can see on this graph, hydropower is very, very efficient in terms of returning a great deal of energy on very little energy recovered. You just have build your dam, and after that, the water flows through the turbines, and it keeps on generating power. Coal is up there too because coal is relatively easy to obtain. Strip mining, scrape off the top of the soil. Coal is in big seams, and you have a significant amount of coal. Oil production, essentially, you can see is shifting. Much easier and cheaper, 70s and 90s, much more expensive in the aughts. The same is true with natural gas. Photovoltaic is out there, all the way down to biodiesel. And there are some arguments that actually biodiesel probably consumes more petroleum energy than it generates in biofuels, which is very unfortunate. So you can see sort of the implications of this in terms of BTU in versus BTU out. And so you need to think about this in terms of what happens. And even solar panels, you can see, are not necessarily as high up as things like hydro. Now, in terms of discoveries, this gets back into what Colin Campbell was looking at. He saw that the discoveries were, possibly significant in the past. Both Kuwait, Saudi Arabia, Siberia, Alaska, Mexico, the North Sea, Kazakhstan, but not much has happened since. So back in 2010, he felt, we might actually be in the peak of production, as you can see. And this is the graph that sort of comes as derived from his concepts. The other issue, of course, is the cost of oil has been rising. It dipped a little bit in terms of the recessions back in 2008, but nonetheless, it's coming back up again. So we do expect that those costs are going to substantially increase. And this goes into sort of the combination of both the exploration opportunities and then, of course, how much we're consuming. And as you can see, it looks as if the actually consumption is certainly greater than discoveries, all the way back as early as about 1980, with a peak happening somewhere in the mid 1980s. And here, in terms of what happens with different conventional oil production scenarios, as well as growth in the economy, what's suggested here is that with different growth levels, there will be different consumption levels. And with those consumption levels come, if you will, the end of the oil reserves. We're probably sitting closer to the 2% number right now. You can see the peak may happen somewhere around 2040, with a sharp decline down into about 2100, 2125. So it's again, it's a sobering number, and I'm not sure anyone has really come up with the clean and ultimate solution, although we need to recognize to do it. Now, obviously, a lot of people come back, well, if we lose petroleum, we'll always have coal. Putting climate change aside, so you don't want to really touch coal with that. Clearly, there are reserves out there, but even coal is going to diminish, and that's what this chart's all about. So again, it just reflects the fact that we live in a finite planet, and we can't always assume that these things are infinite in supply and will always be there. And so, in terms of a sequence, in terms of a vision, a scenario for the future, this is the big picture. You can see that very sharp spike, but certainly by about 2200, oil will be a thing of the past, and we'll have to move on to a different energy source. And of course, we have a lot of environmental problems with oil as well. So we may have to, again, come to the conclusion that some of those reserves need to stay there. And of course, with that maintenance of the reserve comes the crashing of the stock price for oil companies. We're starting to see that with Exxon. Their stock price has been diminished significantly. And essentially, it also reaffirms some of the arguments that have been made by fossil-free Penn, where the students have been saying, look, this is just not a good investment. You might want to keep it. So why don't we get out of it? And why do we encourage that sort of activity by making our investments in this particular area? So what are the alternatives? Clearly we would look at solar, look at wind, possibly tidal, possibly geothermal. The problem, of course, is all of those put together probably won't fill the gap that's going to be created by the absence of petroleum, fossil fuel energy sources. So there's been a lot of discussion about whether we go to fission or fusion. Bill Gates has put a lot of money currently into fission using silicon cooling mechanisms. Fusion, of course, is one of those situations to find it's, we're halfway there in about 20 years, and that always continues to recede. It's almost there 20 years from now. If it ever is successful, it could be very significant. But again, it really is still struggling in terms of its research, but it does fall into that category of innovation. Now, on the other side of that's going to be, what is our demand for energy? So we're going to have to essentially rethink everything from housing to transport to our communities to make sure that we optimize the consumption of resources. And of course, from all of this will be the impact on climate change. Will there also be some impacts that, even though we're trying to mitigate this, we'll need to be able to adapt? And how will that essentially affect all the other sources of even renewable energy that are out there? I'd like to go into the issues of mining. As you can see from my question mark, there's been discussion about sustainable mining. And of course, given the fact that it's also a finite reserve, it becomes a bit of an oxymoron. It doesn't seem to make sense, although there can be responsible mining that goes on there. These are just some examples. You have everything from big strip mining operations to deep mines to blood conflict minerals. Up in that middle picture, you'll have issues with acid mine drainage when those streams turn orange and red. You have impoundment lagoons in the bottom left-hand corner, where the tailings, the spill from mining is held in lagoons until at some point, because of a storm or the natural event, that breaks. And of course, all of those tailings essentially overrun a local community, and with its subsequent effects, as recently happened in Brazil. The impact, of course, on the health of people is certainly paramount. You can see that miners suffer a great deal in terms of the health injuries, in terms of what they breathe in. So it's a illness issue. Obviously, it's a very dangerous process, so there are natural injuries and fatalities. So obviously, we need to think about the social implications of working in mines. So environmental impact, erosions are out there, sinkholes, because you're putting in deep mines, you underplay or undermine literally the formation above it. You'll have collapses that will create a sinkhole above it, or just water moving through karst terrains will essentially cause problems. You'll have contamination of soil, groundwater, and surface water from chemicals, as well as leachate from the mining itself. Clear cutting, of course, sometimes for strip mining is required. And so currently mines are required to rehabilitate programs. And it hopefully allows the mines to return close to its original state. And that's fine for current mining practices, but it doesn't necessarily address all the historic mines that are out there. Invariably, it usually falls to local governments to essentially spring for the cost to minimize the impact it has on the population, which of course is the issue around public health. And it does impact unfortunately, the health of local populations. For strip mining, of course, you have erosion of hillsides, mine dumps, tailing dams, water pollution. It certainly impacts ecosystems and habitats. It can destroy farming areas. It creates problems in urban areas from dust, visual pollution, noise. All these things are part and parcel of living with mines in your area. As I mentioned before, miners' health is up there in terms of explosions, roof collapses, fires, floods, lung disease. Miners for a long time were virtually unprotected. It was understood they were almost expendable. If somebody was killed in the mine, there was always somebody else who was ready to take that job. And so therefore it was a major effort to get mine safety laws essentially passed so that it could be addressed. Now, mining, of course, has been a significant part of the gross domestic product, not just coal, of course, but a lot of different mines, but it's out there. Mountaintop removal, of course, is a blight and an eyesore on the landscape. And you can see, of course, this is the result of what happens there. Shifting gears into agriculture, obviously, climate change is again, the factor as well. Well, what happens when it gets hotter, wetter, or drier? What's the impact of glacier loss of the Himalayas, the Indian subcontinent? If we don't have that constant stream of water coming in from the Himalayas, and it's literally just flash floods. So you have this abundance and absence of water. And what does that do to farming in those areas? How do they manage to deal with that particular boom and bust cycle? Phosphorus is out there, and of course, even petroleum to run the crops, run the farms, are going to be out there. And of course, what areas will be needed for farming? Right now, we're consuming a lot of valuable farm area through suburban sprawl. And how are we going to be able to reuse and reclaim it if we need to? The question comes down socially as to who farms. Will it be industrial farming, big ag, or will it be local and regional farming? Transport of food, will it be moved to a local situation, or will it be global? Do we eat beef, which takes a lot of water, a lot of resource, a lot of grains, or do we go directly to grains? Do we continue to use fertilizers in abundance to a point where they create their own problems with water pollution and eutrophication? Do we continue to use pesticides and herbicides, which essentially not only impact ecosystems, but also then are found in residues in our own bodies? So that chemical body burden in many cases comes from the use of pesticides and herbicides. And can we move away from that, or is that critical in terms of our use for the future? And can we move more toward regenerative agriculture, where the farming approach that we use tends to rehabilitate the soil and allows it to essentially regrow crops? Good example of that recently was the situation where literally cattle themselves can be used in ways that move the stock pen around, so they can, bring down one set of grasses, essentially embed plants into the ground itself, have a capture of carbon in that, move it onto other areas that allow that initial place to essentially regenerate and recover. Fisheries are in the same boat. And again, climate change becomes the big question mark. What happens with warmer oceans? There will be greater oxygen essentially being taken up? What about CO2 being taken up as well? With CO2 uptake, you get acidification, and with acidification, you have problems with shellfish retaining their shells. Fish have problems retaining their bones, so therefore it could be the only thing that is viable in an acidified ocean is going to be jellyfish. Ocean currents are going to be impacted, and what happens when we have an ice-free Arctic Ocean? All these things are out there. Of course, consumption needs to play into it. Can we allow for regeneration? And can we create a aquaculture that allows us to farm our way out of the food fish limits? So sustainable forestry, we move from just cutting naturally growing forests to a farmed industry, such as we do with Christmas trees. What are the impacts of climate change? What about primordial forests? Will they be untouched? Can we afford to keep them untouched? And how do we preserve and protect them against, again, the pressures of an ever-growing population? Palm oil in Malaysia. I worked in Malaysia years ago. I used to drive up and down between Kuala Lumpur and Malacca. And many of those areas were natural forests. Now, the latest time I drove down, this was the scene that I saw, where what had been at one point natural and vibrant and diverse forests are now a monoculture of palm trees. Now, back in 2011, there was the National Academy of Science clearly identified that it does create deforestation. It hurts biodiversity. It does essentially impact the loss of habitat, and it's responsible for about 15% of global emissions. And these are sort of the new farms in Malaysia. Now, of course, it does serve as a source of income and of jobs for people, but it creates its own problems in that regard. It looked about 6% of the total territory in Malaysia, Borneo, Sumatra were taken up with palm oil plantations, with biodiversity losses that range from about 1 to 12% from Borneo to Malaysia. Increased carbon, of course, was emitted, and a total of about 2.3 million hectares of peat swamp forest had been cleared, which is about the same size as New Jersey. Clearly, it's defended, as I've said before. It creates an industry that employs about 20 million Indonesians alone. It doesn't compete directly with food, but it can be used as cooking oil as well as an ingredient in many, many products that you'll find in the stores. Now, again, as the palm oil industry grows in Southeast Asia, it will essentially compete and knock out the native forests with consequences for biodiversity and carbon emissions. So that's my summary for extraction. I'll see you in the next class. Take care. Bye now.